Today, we're going to talk about processing uranium for nuclear power plants. Uranium comes from the Earth, but it comes in the form of a rock. Rocks, as you can see, are not pure uranium. They're a mixture of different compounds. You know that because you can see the different textures, different colors. So you have different physical properties indicating that you have multiple substances in this rock. So, when we're going to get uranium for processing in the power plant, we start with mining operation. This shows a typical surface mining operation. It could be anything, could be coal, but this is a uranium mine. So the uranium, as shown in the previous slide, comes out of the earth. It needs to be chemically and physically processed for use in the reactor. The initial process changes this raw uranium, the rock, into specific fuel pellets that can be packed together into fuel rods and used in a reactor to generate energy. So, after mining the ore, we have to look at the ore. Ore is basically a natural rock that contains multiple minerals. It has a mineral of choice, in this case uranium, but it's mixed with other minerals that we don't want, and they have to be gotten rid of. The first step is milling the uranium ore. Milling takes the ore, the rocks, and crushes it into a fine powder, that's a physical change, that the uranium in the form of U3O8 can be extracted from. So, the process of extracting the uranium from the milling is a leaching process. Once it's done, the uranium compound that we get is called yellow cake. It's called yellow cake because it looks pretty much like Betty Crocker yellow cake mix. The yellow cake itself is not ready for use in the reactor. It too needs to be processed. The first problem that we have is that the uranium in yellow cake is multiple isotopes. All elements occur in multiple isotopes, but in yellow cake, the primary isotope is uranium-238. This is a non-fissionable isotope and is not useful in the reactor. The fissionable isotope that we use in reactors is called uranium-235, but only 0.7% of the uranium in yellow cake and in natural ore is uranium-235. So we need to concentrate the uranium for uranium-235 isotope. So what we'd like to do is get rid of some of the uranium-238. We can do that, but we have a problem. The uranium-238 atoms are attached to the uranium-235 atoms. In truth, in most U3O8 molecules, none of the atoms are uranium-235. They're mostly all U238, but sometimes you get a U235. It's also attached to U238, so how are we going to separate them? We're going to change the U3O8 into a molecule called uranium hexafluoride. The thing to note about uranium hexafluoride is that it only has one uranium atom per molecule. In this picture, you see two uranium compounds. One is a solid and one is a liquid. As they are at the same temperature and pressure, this indicates that they have undergone a chemical change because different compounds have a different physical state depending on their temperature and pressure. In this particular picture, you have a solid uranium compound and a liquid uranium compound. And this would, if it were yellow cake and uranium hexafluoride, be taken in non-standard conditions because uranium hexafluoride is a solid at room temperature. And it sublimes when it reaches 57 degrees. Uranium hexafluoride is not a liquid at all at 1 atm. So to take this picture, the pressure has to have been changed. However, at the correct temperature and pressure, you get the idea. So the fact that uranium sublimes at such a low temperature is actually very useful to us, because we have now separated all of the uranium atoms into single molecules, but we still have too much uranium-238. So the uranium hexafluoride is heated into a gas That allows the molecules to move freely. And you note that uranium-235 has a lower mass than uranium-238, which means that uranium hexafluoride containing U-235 can be separated from uranium hexafluoride containing U-238 by a process called gas centrifugation. The picture on the right shows the gas centrifuge tubes. These tubes rotate at incredibly high speeds, flinging the heavy molecules to the side. The heavier molecules would be those uranium hexafluoride, which have uranium-238. However, the difference between U-238 and U-235 is very slight, so we need to use a process called serial centrifugation to enrich the product to 3.5%, which is what we want. What we mean by serial centrifugation is the tubes are loaded up, rotated, so that the uranium hexafluoride with 238 flings to the side, but not all of it. Some of it's still in the middle. We take out the middle and put it into a new tube and spin it up again, flinging many of the uranium-238 molecules to the side. And then we suck out what's in the middle, and then we do it again and again and again. It takes hundreds of centrifugation steps to get to a mere 3.5%. But that's all we need to run a reactor. The enriched U-235 uranium hexafluoride is a gas. We need to turn it into a solid because it has to withstand very high temperatures in the solid form so that the uranium molecules are close enough together to sustain the chain reaction that a nuclear reactor requires. So the uranium is converted into either uranium carbide or uranium dioxide pellets, which look like this. The pellets are then packed into rods, and the rods are bundled together into an assembly array used in the reactor. That is the end of this presentation, but there's so much more to learn. Nuclear power is a tremendously beneficial source of energy, which is both cleaner and safer than burning fossil fuels.